classical topics. So, I mean, it's mainly focused on the star conjectures. I'll start with a bit about the background of it, as it demonstrates the class number formula, and how it applies to Hilbert's 12th problem on explicit class field theory, and then go through some of the simplest cases. Right, so the star conjectures, and I'm just going to be talking about the abelian case, is a generalization of the class number formula. And I think one of the very interesting things about it is that it gives some conjectural approach to explicitly constructing abelian extensions of number fields. Okay, so brief review of the class number formula you're very familiar with. So here's a Dedekind zeta function for any number field. And in the early 1900s, Hecke proved the various analytic properties of an L function that you might want. And in particular, it also vanishes at 0 with order given by the embeddings of your number field. And the class number formula tells you the leading coefficient, right? The Taylor expansion of a Dedekind zeta function. At 0, the leading coefficient is the class number divided by the number of roots of unity in your number field, and then some regulator, which is a product of logarithms of units in your ring of integers. Now, one way to interpret this result is sort of as like a transcendence or algebraicity result. So this leading coefficient, just otherwise some complex number, the transcendence just comes from logarithms of some units from your number field. And then a generalization or extension of the Dedekind zeta function was formulated by Emil Artin with the Artin-L function, which has more or less the same expression, but for any Galois representation. And okay, it also has nice analytic properties. And we also know exactly to what order it vanishes at 0. So in the 1970s, Stark formulated a few conjectures on the leading coefficients of the Artin-L function. So I'm only going to focus on the rank 1 case. So Stark proved this conjecture when the rank is 0. Now let's assume that Artin-L function vanishes with order 1. So in the abelian case, if I have an abelian extension of number fields and some character of the Galois group, then Stark predicts that the leading coefficient, again, we have 1 over the number of roots of unity, but otherwise we have essentially just logarithms of units with some action of the representation. And to give a slightly simpler version of this, instead of the Artin-L function, we can generalize this to the partial zeta function. So now I allow myself to have some finite set of places of my number field. Then the version of Stark's conjecture here, as long as my finite set of places includes all the Archimedean places and the ramified places, and has at least 2 places, then I can take the partial L function at each element of the Galois group. And so this is equivalent to the previous conjecture. Yes, and so this is also, I'm always going to focus on the integral conjecture, a slightly weaker version that he first posed in 1975 paper. Doesn't specify, like this is just some rational coefficient, but actually it should be 1 over the number of roots of unity. Okay, so this is the integral abelian rank 1 Stark conjecture. And yeah, as I mentioned, one of the nice applications of this is to Kroneker's Jugendtraum, or Hilbert's 12th problem. So this story starts with the famous Kroneker-Weber theorem, which says that every number field can be embedded into some cyclotomic field. So I'm just going to rewrite this. Instead of taking the root of unity, I'm just going to view this as a special value of some complex function, exponential function. Then, so after proving this, Kroneker worked very hard to try to generalize this to imaginary quadratic fields and then to general number fields. So here's this letter to Dedekind in German. For non-German speakers, it's the English. So from this letter is why it's called the Jugendtraum, because he literally calls it his dream of youth is to generalize the Kroneker-Weber theorem. And then this was enshrined in Hilbert's 12th problem. So roughly speaking, just find some complex function whose special values let you generate any abelian extension of an arbitrary number field. So this was done for imaginary quadratic fields in the early 1900s, where instead of roots of unity, we also need special values of the J function and the modular function, the Weierstrass-P function, and this allows you to construct abelian extensions of imaginary quadratic fields. And then this was partially extended to CM fields, right, by the work of Shimura, Taniyama, Wei. For a CM field, the automorphic functions on a Shimura variety allow you to construct some abelian extensions of the reflex field. So we have a partial answer for CM fields. And right, so Stark, after formulating his initial conjectures, realized that his conjectures could give some way to construct abelian extensions of general number fields. So he conjectured that the Stark unit, so the very units that give you the leading coefficient of the Artinel function, also allow you to construct some abelian extensions of a general number field. So this is a special complex function that you need, e to the leading coefficient of your Artinel function. And in Tate's reformulation of Stark's conjectures, he proved that this is actually, if Stark's conjecture is true for a totally real field, then you can get at least all the totally real abelian extensions using Stark conjecture. So not only does it give you some of them, in the totally real case, Tate proved this would give you all of them.
All the absolute value, right?
Oh, yeah, okay. Maybe I should say to some root of unity. Okay, that's some roots of unity, then it's okay. And there's been a lot of progress in the totally real case. So the first case I want to talk about is, for the base field Q. So the first case of the Stark conjecture. So I'm going to let large K be my abelian extension of the rational numbers. I have some a finite set of places S. If you don't care about the partial zeta function, you only want the actual Artinel function, then just let S be the set of Archimedean places and the primes that ramify in K. And I fix some place W. Then if you take the global conductor, or any positive integer, such that all the prime factors are in this finite set, and so that the cyclotomic extension contains K. So I'm just going to let sigma A denote the element of the Galois group for A and Z mod and Z. Stark observed that the partial L function of some element sigma in the Galois group is a sum of Hurwitz zeta functions. So, this curly brace means the fractional part, and the Hurwitz zeta function is this infinite sum of whatever your rational number in the argument is. And in particular, it has a special value at 0 of just 1/2 minus the argument, the rational argument. And I'm just going to focus on the special case when K is a real extension. Stark sort of took like a symmetrized Hurwitz zeta function. I just take the Hurwitz zeta function and then I add itself with minus t. And then he proved that, okay, this has a special value formula at 0 in terms of some cyclotomic units. This is all very classical, but then he used this for the partial zeta function to show that the partial zeta function, the first derivative at 0, is negative 1/2 times the logarithm of this unit. So, and this unit is some cyclotomic unit. So Stark proved his conjecture in the first case when the base field is Q. And the unit is always going to be some cyclotomic unit, and you can describe this explicitly. And he also showed that adjoining this always gives you some abelian extension. So this was his right, his approach to Hilbert's 12th problem. And now let me turn to the other case, the other classical case, which is when the base field is an imaginary quadratic number field. Right, so keep in mind, both of these are cases where we already have an answer to Hilbert's 12th problem, but Stark wanted to consider if his conjecture actually works and verify in these cases. So now little k is an imaginary quadratic number field. And so he takes the same kind of idea. So instead of capital N being the global conductor of the number field, now we have some, I mean, it's essentially the same thing. We have an ideal whose prime factors are in S. So that the ray class field contains your abelian extension. And then, you again use this surjection from the ray class field to the Galois group of the extension you're looking at. Okay, and then, not super important, there's the decomposition of the Galois group explicitly in terms of the fractional ideals and principal fractional ideals. And then if I let this be the Artin map, so the Galois group element corresponding to my ideal, then Stark showed that you can decompose your partial L function for an extension of the imaginary quadratic number field in terms of these L functions, the zeta functions of A, right, of your ideal A. Okay, so I'm just moving that up to the top. And now, okay, take some element of the upper half plane and some positive rational number that generates the inverse of each ideal A times your fixed ideal N. And take the classical Eisenstein series. And if you apply it for this tau and this C, if we apply it to this tau and this C, and the Kroneker's limit, second limit formula tells you that, right, the Eisenstein series at tau and C is a logarithm of a Siegel unit. The Siegel unit is this large product of exponential functions. Okay, so I move this up again. And okay, so then we have some expression for the partial L function in terms of these logarithms of Siegel units, which a priori maybe we don't know are actually units. But this function that defines a Siegel unit is an automorphic function. And it's in particular the holomorphic function on x1 to the n. So something of weight 12n. And okay, as I mentioned, I have lots of slides with technical text that I didn't. The point in the end is that okay, we have now some special value of some holomorphic function on a modular curve that explicitly gives us the partial L function.
Sorry, is phi just a theta function?
The power of a theta function, right? Yeah.
But it's a Jacobi form?
Yeah, so this is the thing in Siegel's. Yeah.
Okay.
What is F? The bottom formula?
Oh, F is just what I'm defining the phi to the 12n.
Oh, sorry. Yeah.
Sorry, what is S on the right-hand side of the screen?
What is S?
Where does S show up? Like
Yeah, I think
the little s.
This?
No, S, like the parameter S.
Yeah, you should have.
Oh. Yeah, sorry. I'm now taking it as 0. Yeah, sorry. I copied and pasted this. Yeah, this should be the special value of it as 0. Sorry. Prime and at 0. And then Stark uses CM theory, which I already point, to show that this value of this holomorphic function is actually a unit. Right? So it's some algebraic integer in some abelian extension. So,
And also in the above, right? In the middle equation, it should also be S LS prime, but zero, because I don't see S on the right.
sorry, yes, that's also, yes. Yeah. Yes. Yeah, both of these should be ls prime 0.
So just to clarify here again, so CM theory is still better than Stark's conjecture because it gives you a formula for the actual unit, whereas Stark's conjecture, if you exponentiate, then you would just get the absolute value of the,
Yes. Yeah.
from which you wouldn't be able to reconstruct necessarily the unit, right?
Yeah. No, that's a good point. Yes. So, right. So for Stark here, the CM theory exists, and he's using it to prove his conjecture, and just verifying that it gives, up to root of unity some answer to Hilbert's solved problem. But CM theory already gives you
Exactly.
Hilbert's solved problem.
Yeah. You wouldn't solve Hilbert's 12 with Stark necessarily, even in practice, right? You would still use CM theory.
In this case, yeah. Yeah. The idea of Stark is to generalize this, to use this for a general number field where we don't have CM theory, but he's testing in the CM case that his idea works. So this is just all to give a sketch of Stark's proof that indeed the leading term of the Artinel function is given by some unit, some logarithm of some unit, and in this case it's given by some product of these Siegel phi functions, these Siegel units. And he also checks, so this elliptic unit gives you an abelian extension. But of course, we kind of already know this by CM theory. Okay, so now let me move on to the next case, which is the next complex case, which is when little k is a complex cubic field. So before I do that, I guess I should mention the other direction in which you can go is for little k to be a real quadratic field. But I guess I don't want to focus on that so much, but of course this is like the subject of the works of Dharma and Kakte and Dasgupta on Brumer Stark and on like Stark-Huebner points. This is kind of orthogonal to that in considering the smallest complex case. Okay, so now let me let little k be a complex cubic number field. Right, so a cubic field can either be totally real, or it can have one complex place and one real place. Okay, and then let me let large k just be some finite abelian extension. So this case of the Stark conjecture is a subject of several works already. So maybe the most notable starting point was the thesis of Dasgupta in 1999. Where in particular he takes a specific example of some sextic extension of some complex cubic field, and he verifies, he has some conjectural formula for the Stark unit, and he verifies that this gives the leading term of the Artinel function up to 25 decimal places. And then immediately after that, there is this paper that verifies a lot more examples with much more computational power. That Stark's conjecture is true for many more abelian sextic extensions. So if you recall, in the imaginary quadratic case, Kroneker's second limit formula plays an important role in constructing this unit. I mean, you relate this Eisenstein series to these Siegel units. So these papers of Bump and Goldfeld, I think Wren's thesis at Rutgers, and then Bergman, Charlotte, Garcia, they propose these new analogs of the Kroneker limit formula for complex cubic fields. And then, so Dasgupta gave conjectural, like a precise formula for the Stark unit in his example, and then Wren-Check in 2009 and Bergeron, Charlotte, Garcia also give explicit formulas, conjectural formulas for Stark units for complex cubic fields. Sorry, I should say the elliptic gamma functions is just for the last one. So this is a summary of what's been done so far. So I want to get into maybe the actual arithmetic of complex cubic, that's particular to the complex cubic fields. So I guess this really following the work of Hasse in 1930. He really studies the algebraic number theory of complex cubic fields. So for every complex cubic field, if you take the discriminant, you get some imaginary quadratic number field called the quadratic resolvent, which I denote by F. And the Galois closure of the complex cubic field is the compositum of your complex cubic field with this imaginary quadratic number field. And then you get some S3 extension of Q. And now, okay, let me focus on the specific case where my finite abelian extension in particular contains that quadratic number field. So, okay, here's my diagram trying to summarize what's going on. So little k is my complex cubic field. So all the vertical lines are cubic extensions. F, right, is my quadratic, imaginary quadratic number field. So all these diagonal ones are quadratic extensions. And then k is my arbitrarily large abelian extension of little k that contains F. So these horizontal lines, could be some very large Galois group. And then I've also identified, so I've also written down the L, which is the maximal abelian subextension of K. And then I've also written down the maximal totally real subextensions. So hopefully the notation makes it clear. The K plus is maximal totally real part, so we don't get that complex conjugation from this diagonal lines. And same with L plus for L. Of course, Q is the maximal totally real subfield of an imaginary quadratic, and then little k for its Galois closure. So I'm going to keep this diagram on the right the whole time, because there are a lot of letters. Okay, so I want to use the fact that the capital K contains both little k and this imaginary quadratic number field to try to decompose its Artinel function.
So there's big K cyclotonic.
Yes, by cyclotomic I just mean, so it's some abelian extension that contains the imaginary quadratic number field. I'm using them synonymous. Okay, so moving in the direction of Stark's conjecture, let's take some Galois character chi. And so I'm going to take two associated characters. One is so the Galois group of capital K over little k is isomorphic to the Galois group of the same thing below, right? So chi q is just chi, but viewed as a character above q. And then chi k is a restriction of that, the restriction of not chi q, of the restriction of this character. Sorry, this should be these should both be little k. And, sorry. Makes sense.
Doing K over L. K over big L.
No, I want the restriction of L over Q to L over F. Sorry, the letters are totally wrong in the second bullet. Yeah, sorry. If I wasn't dealing with the Swiss police, I think I would have fixed that. Yes, okay. Oh gosh, okay. Chi k is the character over the imaginary quadratic number field F. So L over F. Okay, actually, so it's not both of these k's should just be f's. That's it. Okay, and now, okay, these are not actually, so I picked some character of, just of this order 2 thing, so complex conjugation, I mean, the Z-mod 2Z. So I take the non-trivial character of that is eta, and then omega is the non-trivial character of this cubic thing, right? This degree 3 cyclic thing. So you pick one, you have 2 choices. Okay, and the whole point of this is that if I take, so the induced representation of chi, okay, so chi is on here, and I induce it to a representation over Q, then I get a decomposition of, so I can express it as a tensor product of the character over L over Q, and then times the induction of the trivial character from little q to the cube. And so this induced representation decomposes the direct sum of a trivial character and some character of this cyclic thing of order 3. And so I get my character, direct sum with induced representation of chi, oh, I have the F correctly here. Chi restricted, so the character over the imaginary quadratic.
Something here looks weird because always an induction of character from quadratic extension. So on the upper row it was dimension 2, but on the second row int kq is a 3-dimensional thing. So something here doesn't match.
Say that again.
On the lower row, O is chi q, which is 1-dimensional, tensor product with an induction from a 3-dimensional thing.
Oh,
So
maybe
it's a
this,
3-dimensional thing.
maybe this should be.
fq is a 2-dimensional.
Oh, sorry, this maybe should be an F.
I think there's just a third factor with omega squared. Like on the very right-hand side, maybe there should be, or maybe not.
No, what is O? How do we find rho to begin with? The induction from Q to O.
So I want the induction of this to.
It means from Q to K, from to little k perhaps?
It's okay.
Rho is induced from K to Q.
Yeah.
This is K.
Yeah. Chi is a character of K.
Yes, yes. Yeah. So here to here, like this extension
Yeah.
to this extension. Then I get this character. Oh, yeah. Okay.
Yeah.
Yeah. So there should be a little K. Yeah. Okay. Thanks. Sorry. It's a terrible place to mislabel all the letters. Okay. From this decomposition of the actual representations, right? I use the nice properties of art and L functions with respect to induction and direct sum. Then my L function for chi, which is the same as the L function for rho, or from the induction, is the product of the L function of my character that's over Q and an L function of a character that's over F. Right now, and then the point is, okay, maybe we can try to use the star conjecture, which is known for each of these separately, to say something about the star conjecture for here.
So these have degrees 3, 1, and 2, just to clarify.
Sorry, what has degrees?
The L functions on the bottom line. They're absolute degrees over Q, or are they 3, 1, and 2? Or I guess
Yeah. So this, this is L function over this is for the cubic. This is for Q, and this is
Okay, thanks.
Okay, and then so this is just for the normal L function. If you want to do for the partial L function, this decomposition holds. These are some mild technical conditions, but so this decomposition holds within S almost always, unless one of these two things doesn't happen, which I think is rare. But
But does it actually fail if those conditions don't hold, or is it just harder to prove, or what is
No,
it?
I think it's a if and only.
Okay.
Right. So if I want to do this for partial L functions, partial zeta functions, then I assume that there's some rational prime. So if I have some rational prime of Q that ramifies in L, then S needs to contain all the totally ramified places above that rational prime. And also, there is some other, potentially other rational prime that's totally ramified in the complex cubic, but unramified in L. Or if that doesn't happen, then I need S to contain a place over that prime, over a prime with maximal residue degree. Okay, so anyways, some ramification conditions for S containing some certain ramified primes. Yeah, sorry.
So the isomorphism of the color group, big K over small k, and isomorphic to over Q, you always assume it, or is it always true?
No, I think in this case it should be true. In the setup I have, it should be true. Yeah. And in fact, so not all of these are Galois, but when they are Galois, they should be isomorphic, like to the parallel lines. All the Galois groups for parallel lines are isomorphic if they're Galois. Okay, so just summarizing again from the last page. Now we take, again, okay, this is the same thing that Stark used in the cube case. So now I want to apply to my decomposition the Hurwitz formula for the character over Q, which I've written here. And now beta is some element of the Galois group of K plus over K, over little k. And then Stark's theorem, which I've written now, which is for big K over F. Right. So basically I'm trying to apply Stark's theorems for these two components, 1 over Q and 1 over F. And this is over each Galois group element, and I want to combine these in a convenient way using this complicated element of the group algebra. There's an exponent 1 over n. So this is actually not a problem. Combining these identities and then doing a lot of technical work, I can get some integral element, some actual element of the group algebra, and such that the leading term of the Artinel function is given by the logarithm of, this is the unit for the imaginary quadratic field, so some elliptic unit, to some integral thing. So still essentially some elliptic unit. And now I have a number of roots of unity squared of L. So it's not exactly the same as in Stark's conjecture.
Is sigma chi or something else?
No, sigma is an element of the Galois group. Oh, sorry, I switched at some point from chi to sigma. So if you want this for chi, then I take a sum over all sigma of this thing, and then chi of sigma. But actually, I can do it just Galois group element by Galois group element. So I can do this even within the whole character.
That is the single elements by taking the characters and cancelling them out by orthogonality of characters.
Oh, yeah, you can, yeah, exactly. So you can go from one to the other equivalently.
Or which one you get first? You get first the results from the characters, this algebraicity result, and then you go to the individual elements, or the other way around?
In this case, so I wrote this for individual sigma, but yeah, they're equivalent. Yeah. Okay, so in particular, this so this implies this thing that looks like the Stark conjecture for the complex cubic field. Just the difference is I have WL squared, and I get some explicit elliptic unit, which is a power of the Stark unit up to a root of unity. And okay, so this is a case of the rank 1 Stark conjecture for complex cubic fields. And it's a slightly more complicated case where the character chi, so in the previous case, chi is odd. So the L function vanishes with order 1. Stark's conjecture is also is a version for every rank. And if chi is an even character, then the L function vanishes with order 2, and the Stark conjecture becomes something about the second derivative as 0. And Stark predicts that there should be 2 Stark units whose logarithms give you the leading coefficient. Essentially, the same proof as what I just outlined also gives the Stark conjecture in this rank 2 case, where now I have, so before I only had an elliptic unit coming from the imaginary quadratic field. That's because the L function for the imaginary quadratic vanished with order 1, but the, let me go back. In this decomposition, so for what I was talking about, this vanishes at 0. Sorry, this doesn't vanish at 0. This vanishes at order 1. So that's why I didn't get a unit. I had no cyclotomic unit from the rational part, but I had an elliptic unit from here, right? If I do products formula for the derivative. I had L of 0 times L prime of 0. In this rank 2 case, I have L prime of 0 times L prime of 0, which means that I get 2 units. So I get some cyclotomic unit from Stark's conjecture over Q, and I get an elliptic unit for Stark's conjecture over the imaginary quadratic. Okay, and again, I've written it for some u as opposed to epsilon because there's this difference of a root of unity and a power. And okay, I would have had to make like some 4-dimensional cube drawing, so I didn't. But this rank 2 case happens if my big extension is a compositum of the imaginary dihedral, the imaginary quadratic field and some the complex cubic times some totally real thing. Maybe it would have been easier if I just wrote chi even and chi odd. Okay, so there's one famous example where this applies to. So Dasgupta's thesis, as I mentioned, he gives some explicit example, and he verifies Stark's conjecture up to 25 decimal places, and also tells you what the unit should be, the Stark unit should be. So this is his example. So this cubic polynomial, x cubed minus x squared plus 5x plus 1, the root of that gives you some complex cubic field. The imaginary quadratic field in this case is q adjoint square root of minus 3. It has a Hilbert class field of the complex cubic adjoint 7th root of unity plus 7th root of unity inverse. And then the sextic extension he looks at is the Hilbert class field adjoint a 3rd root of unity. So for q adjoint the beta from the complex cubic field, and then zeta 7 plus zeta 7 inverse from the Hilbert field and zeta 3. So in this case, so I think in this case the prime 3 comma beta plus 1, where this is beta, satisfies the condition I mentioned before on S, where you don't want some totally ramified thing, it's a maximal extension. So Dasgupta conjectured that this degree 6 polynomial, one of the roots should be the Stark unit times the root of unity. And he verifies that up to 25 decimal places. So he calculates all the roots and then checks it against the L value. Right, as I mentioned, this example satisfies all the hypotheses of the theorem I just mentioned. So epsilon is the Stark unit, the unit that Stark predicts. So the Stark unit up to root of unity should be root of this polynomial. And now I have some explicit elliptic unit in terms of these Siegel functions. So with good enough computational power, I check, okay, maybe some, in this case, I think it has 6 roots of unity. So some 6th root of my elliptic unit times another root of unity, it would be a root of this polynomial, and I know for sure that this is an algebraic unit. So actually computationally, right, if this thing I know for sure is like less than 1 or something, then I would know this is actually a root. Not just up to some decimal precision. Okay, and finally, let me go back to Hilbert's 12th problem. So from those two theorems, the rank 1 and rank 2, you can immediately get a sort of an application to Hilbert's 12th problem, not for any cyclotomic extension of a complex cubic, but for at least for a cyclic one. You can immediately get that, okay, assume none of the places in S are split, then your big extension was generated over the complex cubic exactly by the unit from the partial L function. And in the rank 2 case, then you describe the more extensions that are appearing here. Yeah, okay. I said I would keep it short. Thanks.